we say that the garbage collector disposes this node because it no longer exists. And that's how we remove it. So whenever you want to like skip over a link or something like that, you can just set the .rest to be the .rest, which means to skip over that one. Okay, and then some, last but not least, we have some coding practice. So if you want to find the length of a linked list, you can have this set of code. So basically, we're going to check if the link that we have right now is empty, because of course, if you're just given the example of an empty list or empty link, then it has the length of 0. But if it's not empty, therefore it has either one link or more than that, then we're going to return 1 plus the recursion of it. So we're going to usually recurse on link.rest because that's going to be the next link, and then we want to apply the same process for each of the links. So for example, with this example over here, we have 2, 3, and 4, and it's going to add, well, first it's going to call, let me try to draw the call stack. So it's going to call find len of 2, and then how am I going to represent this? Okay, so it's going to call it on 2 ... and what I mean by 2 ... it's just the rest of the list. And then it's going to add, basically this is going to evaluate to 1 plus find len of 3 ... which this becomes 1 plus find len of 4 ... Before ... is just, let's see, it is 1 plus find len of empty. And we know that when it's empty, it's just 0. So that's how we get 3 in the end, because we're going to add up this one, and this one. And then we can also add 0, but adding 0 is just the same thing as adding nothing. Okay, so that's how we find the length of a linked list. So notice here that this was our base case, and this is a very natural base case to use because when we want to stop the recursion, it makes sense to stop at the end of the linked list, which is typically denoted by the presence of link.empty. So usually when you see that your link has become link.empty, or that it was passed in this link.empty, you want to do that base case, whatever that operation would be. And then our recursive step is, I think it's very similar to an example we did in class before. I think it was like count primes or something like that, where we just add 1 every time we see a link, and then we move on to the next link and try to see if that is also a link. So that is the aggregation part, where we're adding up the ones at the very end. Alright, so just a quick note about some other things in linked lists. So we talked about removing here, and one of the things that we like linked list for is that it's very efficient. So you can see here that when we removed a link, it was very efficient because all we had to do was just reset a pointer. And whereas in regular lists or other lists, you might have to, take one out and then move all of the rest of the elements behind it up or something like that. So what I mean is, like, let's say you have 1, 2, 3, 4, 5. Imagine that, like, these are just like, people or something like that. Oh man, stick figures. Okay, so imagine there are people, and we have to take one of them out. So what we mainly have to do is move one up, 1, oh, I forgot to move the numbers. Okay, 1 up, and then 1 up. So it's just like an analogy, but sometimes in lists you have to like manually resize them. Whereas linked lists, all you have to do is reset a pointer, which makes them very fast in that case. And another thing you can do really fast is add another link. So if I wanted to add a link over here, let's say I want to add 1 to the very top or very start, what I can just do is make a new link with 1 and then have it point to my 2 link, and then make sure that link is pointing to 1 instead of 2. So that was just 2 steps, and that's really fast. And then another thing is if I want to instead not add to start but somewhere in the middle, I can just say, like, let's say I have 2.5 here. I can reset 2's.rest to point to 2.5 and have 2.5 point to 3. So that's basically it. It's just 2 pointers that are getting reset. Or in this case, I guess this one's not being reset, but all we had to do is reset links 2, and 3 was already pointing to 4. So it's really efficient to do this in a linked list because all we have to do is change the pointers. Okay, so I think that's it for linked lists.